Yeah, thanks everyone for coming back. So yesterday I spent the whole time talking about triangulations of convex arrangements of points, and everything that I mentioned was pretty classical, I think. Today is the first day, I think, where we venture out into something which was new to me up until about a year ago. And yeah, we'll see what that has to do with representation theory in maybe the next few days. So here are some non-convex arrangements. And if I, without telling you anything, I've simply triangulated them. And the definition of a triangulation is the same. I mean, I take a bunch of edges that are non-crossing and a maximal such set. Okay, so if I were to talk about plain old triangulations, I would give exactly the same definition. But it's we can kind of immediately start to see that triangulations of not necessarily convex arrangements don't maybe have the same nice properties as you had seen in triangulations of convex arrangements. In particular, let's look at, so today it's going to be a lot of examples today, and let's look at this thing here. So the triangulation of 4 points in non-convex arrangement. Now, previously, we had noticed that, of course, each edge is either external or internal. And in the previous situation, every internal edge was flippable. But already we see here that that's not the case. I mean, this edge here, if you remove it, there's no flip. In fact, this is the only possible triangulation of this configuration. So that's kind of unfortunate. I mean, in the arrangement with 5 points, you can do a little bit better. This edge, for example, is flippable, so I could flip it to this other edge here. But that's more or less the only. No, wait. There's another. This edge here is also flippable. You can check that yourself, but the other 2 edges are not flippable. And the main reason for this, obviously, is that if you remove some of these edges, the figure that you leave behind is still a figure made up of 2 triangles, but it's no longer convex. So it doesn't have 2 internal diagonals, so you can't just. So what do we do? I mean, this is something to reckon with, maybe. And one thing you could try to do. So okay, let me write down the problem. Problem number 1. Not every internal edge is flippable. And the problem number 2, I mean, maybe these aren't problems depending on your point of view, but problem number 2 is if you try to count how many edges there are, you no longer get 2n minus 3. So in this case, when n equals 4, you have 6 edges, and 2n minus 3 was can't do this in my head for some reason, 5, sorry. So this triangulation here has kind of 1 more edge than you would have expected for the convex configuration. And actually you can do, so the count that we did with the Euler characteristic, you can modify and figure out exactly how many edges such a triangulation has. I'll do that in a minute. So the problem number 2 is that the number of edges in a triangulation kind of depends on the configuration. So it depends on the configuration, not just on the number of points. Okay, so let's quickly warm up by computing how many edges we would have in such a situation. Let's do the calculation from yesterday once again. Okay, so once again, let's suppose we have n points. now I no longer know what the arrangement is. It's generic. Okay, I don't want any three. I want no three on a line, but other than that, anything goes. So typically this is called endpoints in general position. And let's suppose we have E edges and F triangular faces in a fixed triangulation. Okay, so our Euler's formula from yesterday goes through without any problems. It's the same. So it's going to be n minus E plus F equals 1. Okay, and now we need to figure out how to produce another equation so that we can solve some things. And so yesterday, the thing we did was we said, okay, each triangular face has 3 sides. And so we count the number of sides in that way. And then we count it using some other way, using sort of like figuring out how many times each edge gets counted and so on. So we can try to do the same thing here. So once again, each face has 3 sides. So once again, we can start off by saying 3F equals. So this is 3 sides per face. And this time, what should we do? So each face has 3 sides. Each side, each edge gets counted. Most edges get counted twice because most edges border 2 triangles. The only edges that don't get counted twice are the edges that lie on the outside. So now we don't know how many edges lie on the outside. So we need a new variable for that. So I think I'll just say, don't know how I wrote it in my notes, but it's most edges border 2 triangles. But then you have to subtract something. Minus, I'll just say minus m, where m now is the number of external edges. And that, of course, depends on the configuration. Okay, so you get these 2 equations and you can solve them. And I'll just tell you the answer. Or maybe someone can solve them for me. I don't know. What do I have? Okay, so the number of, or maybe I should have, well, it doesn't matter. So the number of, okay, so the output of these 2 equations is that the number of edges, so E becomes, so yeah, all right. So E becomes 2n minus 3 plus n minus m. And maybe I should have, I should have said m is the number of external edges, but k is the number of internal edges or something. So I'll call this thing k because that's what ends up being important. Oh, I'm sorry. The number of internal vertices is what I wanted to say. So the number of external edges is the same as the number of vertices on the convex hull. There are n total vertices. N minus m is the number of vertices that are not on the convex hull. Okay, so that's maybe like it's better to introduce this k, so it doesn't matter. And then f ends up being again n minus 2 plus n minus m, or I can write this as n minus 2 plus k. Okay, so this is again not complicated, just a version of what we did yesterday. Okay, so this number 2n minus 3, I'm deliberately writing it in this form because I think I want to emphasize that this number 2n minus 3 is going to show up time and time again. Yeah. Say again. 2n. Yeah, okay. Thank you. Some confusion for Hawaii, some confusion which ended up being okay. So good. So but now I want to move on. So I I don't like this somehow, because I don't like the fact that we have to carry around this K, and yeah, I don't want this. So I'm going to choose to do something different. I'll make a remark here. Of course, you can, so if you wanted to continue with something like this, you could, of course, do things. So one thing you might try to do is say, okay, well, this edge right here is not flippable, but fine, I'll delete the condition that my edges have to be straight lines. I could make them curves or something. And then I can say, okay, if I want to flip this edge, I simply add in the curved edge like that. So I could do other things. And indeed, people do other things like that. I mean, so those are called like ideal triangulations or something. So you could do that, but that's not what I'm going to do. Okay, so instead, the direction that I'm going to go in is the direction of pseudo triangles. Oops. So this is fine, but not great for my purposes. So instead, let's introduce pseudo triangles. Has anyone seen these before, just out of curiosity? So I had never heard of them. Okay, good. So what's a pseudo triangle? I'll draw it, and then I'll draw some of these, and then I'll define them. Okay, so here's a pseudo triangle. Okay, so that's a pseudo triangle. A normal triangle is also a pseudo triangle. And now from this, you can maybe guess what the definition should be. A pseudo triangle is a polygon in the plane, a non-crossing polygon, whose convex hull is a triangle, and all of the other edges kind of curve inwards. Okay, so that's the definition. So a non-crossing implies that it has a well-defined inside and an outside. Okay, so that's what I'm interested in. Is a non-crossing convex polygon such that its convex hull is a triangle. And I might relax this definition as we go on a little bit. I'll explain when we get to it, but for now that's what I want to say. Its convex hull is a triangle. And two, every internal angle other than at the convex hull vertices is reflex. Okay. Yeah, sorry.
Why is this like the pseudo triangle convex?
Why is it convex? It's not convex, but its convex hull is a triangle. So if its convex hull would be. Oh, I should just delete that. Sorry, that was a mistake. Yeah, just a polygon. Definitely, probably not convex. Okay, good. So, but I mean, the definition is wordy, but you can draw them. So it's not at all clear why I'm interested in this right now, but let's just keep going, and then we'll figure that out as we go along. So now, what I want to do is, if I have an arrangement of points in some general position, I no longer want to cut it up into triangles, but rather I want to cut it up into pseudo triangles. Okay? So let's, we will now be interested in pseudo triangulations. And of course, triangulations are special cases of pseudo triangulations. So here's definition. A pseudo triangulation of a, for now, generic arrangement or configuration of endpoints is a subdivision of its convex hull into pseudo triangles. Subdivision by edges, of course. I'm sorry? Oh, sorry. Yeah, if I should explain that. The convex hull vertices means if you have an arrangement of points in the plane or in space, actually, is the convex hull of a configuration of points is the smallest convex figure that contains all the points. Okay, so and convex, of course, means that if you have, so a convex set is a set in which if you have 2 points in the set, then it's the line segment joining them also is contained in the set. So I'll write this in a minute, but the convex hull of the arrangement on the left here, right? If you think about it, it's going to be this triangle. Because all of this stuff here necessarily has to lie in the convex hull because you see this point and this point is already in the set. So this segment had better be in the convex hull. So if you throw in kind of all of the line segments of points that are already in the figure and kind of just take closure under this operation, you'll get a triangle. Does that make sense? The convex hull vertices are exactly the vertices that appear on the boundary of the convex hull. No, so its convex hull has to be a triangle, so it has 3 vertices. Yeah, so a pseudo triangle, if you look at its convex hull, it's like, basically it looks like a triangle, but you've like pinched the edges inwards. So you can make similar definitions for pseudo quadrilaterals, pseudo kagons, etc. Any other questions? Okay. Okay, so right, so I didn't write the definition of convex hull, but if you don't know it, I just said it, but you can come and talk to me or talk to someone else. Okay, so it looks like we haven't really gained anything because a triangulation is also a pseudo triangulation. So why do we care about something like this? Okay, so what did we gain? But let's suspend disbelief for a little while longer and keep going. Okay, so let me give you some examples. So let's look at these pictures here. So of course, all of these are still examples. But I could now, I mean, I have more things to do. So I could, these are just plain triangulations, but I can make them pseudo triangulations by deleting even some edges. So once again, of course, in a pseudo triangulation, the convex hull edges are necessarily in the pseudo triangulation. But if I delete one of these 3 edges here in the middle, that's still a pseudo triangulation because this figure here, so if you're not used to thinking about pseudo triangles, it might take a little while, but this figure here is a pseudo triangle. And then what can I do to this quadrilateral, maybe I could, you know, I can like delete this edge here, or I could delete this edge here. So you can do various things. Yep.
Sorry, why can't you delete, so the first picture or whatever, why can't you delete that top edge? Because,
This one,
no, the next
this one, I could.
one. The next
This one,
one. Oh,
this one.
cool. Yeah, that one.
That one. If I, yeah, you're right. Okay, I should be more specific. I always do want to include the outside edges. So maybe I should add that to the definition. Oh, not here, sorry, down here. Moreover, we always include, yeah, you're right, of course. The convex hull. So I want maximality is the idea in some sense, although it doesn't make sense for the definition. So I will artificially, for now, artificially include the convex hull edges. Okay, good point. So here are some examples of pseudo triangulations. So let's do our Euler count again, because that's fun. So let's again count the number of edges, faces. So this time things are even more complicated because each face does not necessarily have 3 edges. So we'll see what to do about that in a minute. So again, suppose we have endpoints. Once again, for simplicity in general position, I'll get to non-general positions in a second. Well, maybe not in a second, in a few minutes. And consider a pseudo triangulation. With E edges and F pseudo triangular faces. Okay, so yeah, I'm trying to do some count, and of course, like last time, I will need some auxiliary variables eventually, but let's see what we need when we get to it. Okay, so the first equation goes through as usual, n minus e plus f equals 1, no problem. But now, what the heck should we count? Because each triangular face has, I don't know how many edges it has. You know, it doesn't necessarily have 3. So what can we do? Are there any ideas? So the trick is not to count the edges at all, but to count the angles, because each pseudo triangle still has 3 convex angles. So that's the trick. Okay, so I mean, you could maybe do other things, but here's a statement which is essentially part of the definition. Every face has 3 convex angles and several reflex angles, which we will have to deal with, but this is what we'll use. So let's count the angles. So the number of convex angles oh, convex means less than pi. If anyone? Yes. So the number of, so when I say angles, by the way, of course, I mean like, you know, like all of the angles formed by various adjacent edges, right? So this is an angle and this is also an angle. etc. So the number of convex angles in the figure is exactly going to be 3 times f. We also need the number of reflex angles in the figure. And for this, I don't know what this is. So we'll need an auxiliary variable. So let R be the number of reflex angles. And just to make sure we're all on the same page, there are reflex angles that are on the inside, and there are reflex angles that are on the outside, but we count all of them. Okay, so including the outside ones. I don't know if Euler proved it actually. It's called Euler's formula, but yeah. Oh, so this is okay. So this is not. This has nothing to do with pseudo triangles. This is a formula for planar graphs. So this is true for every planar graph. So it doesn't matter that we are cutting things up into pseudo triangles or whatnot. As long as the graph that we're drawing is planar, non-crossing on the plane, this formula is true. So this is why it's always true for any of these counts that we're doing. Right. Okay, so including the external ones. I can't, what have I done? External ones. So, okay, so then the total number of angles, therefore, is 3f plus r. And let me take an example here just so that we have something to look at. Okay, so I have a whole bunch of angles here. So I've got these convex angles, and I have these reflex angles, and I've counted them separately. Mr. Convex angle here. And I said that the total number of angles is 3f plus r, but now, sorry, but now, of course, you can see how many angles emanate from each vertex. It's the number of edges that go out from each vertex. So it's the valence of every vertex. And so you can relate this number 3f plus r, you can relate to the number of edges. So this is in fact, but also note that every vertex borders valence many angles. Okay, and so if you count overall the vertices, then the sum of the valences is counting all the edges, but it's counting each edge twice. Okay, so this on one hand is the number of angles, but it's also two times. I'll give you a minute to make sure that that makes sense. Each edge has two vertices. So now that's good. We have like one extra variable, but more or less we have an equation that relates f and e. So let's plug that in. So on one hand, we have n minus f plus e. Did I do that right? N minus, thank you. I just had a moment. Yeah, thank you. And then 3f plus r equals 2. Okay, so then let me try and solve this in real time. So 3f is 2e minus r, and that's also equal to 3 plus 3e minus 3n. And if I move things around, what do I get? I get e is 3n minus 3 minus r. And suggestively, let me write this as 2n minus 3 plus n minus r. Okay, so the number of edges in a pseudo triangulation only depends on the number of reflex vertices in the pseudo triangulation. But now, like this formula here, this beautiful expression suggests exactly what we should do to make our life nice. And the idea is that we impose r equals n. So if we just artificially stipulate that we only want to think about pseudo triangulations which have n reflex vertices, then great, then the number of edges is constant. I mean, it's sort of, yeah, so it doesn't depend on the configuration anymore. It just depends on the number of vertices. So this is exactly what we're going to do. So this suggests that we restrict to the case r equals n. And what does this mean? This means you need a reflex vertex. I mean, sorry, every vertex has to have a reflex angle. So okay, so this is like some motivation for why I'm doing this. It's not, it still doesn't explain why this is nice at all, but let's again keep going. So let me look at this example here. Actually, I'll redraw it. So of course I have the convex hull edges, but I'm now no longer allowed to put all three. So this is disallowed because if I did that, then every, like the central vertex would no longer have a reflex angle. So that's bad. So I don't do that. And now all of a sudden I get three possibilities instead of the one that I had. Actually, no, I had several before, but yeah, but I have these three possibilities. What's the other one here? Okay. And they have the correct number of edges and somehow life seems better. There's an unexpected consequence, which like just by doing this sort of Euler count, etc., you may not have predicted. I mean, I certainly didn't know why that should be true. But if you stare at these three pseudo triangulations for a minute, these are restricted pseudo triangulations where every vertex has a reflex angle. The outside vertices always have reflex angles. You just have to worry about the inside vertices. And now let's think about flipping. Okay. So now if you think about it, well, I haven't told you how to flip anything, but if you just stare at this for a second, look at this picture here on the left, pick your favorite internal edge, delete it, and see, can you add in something else to make another pseudo triangulation with this property? And indeed you can. There's only one other thing you can add in. And then similarly, if you had picked this one, deleted it, looks like there's only one other thing you can add. So it looks like whatever flip means, I haven't told you what it is, but it looks like there's some sort of flipping going on. So this is cool. So edges are flippable, question mark. Yep. These meaning, yes, for any configuration you mean. It's not, maybe it's not clear. No, well, yeah, oh, sorry, thank you. So the question was, is it clear that these always exist? I think yes. What you can do is you can take whatever configuration you have, just throw in all of the edges to make, kind of form a triangulation. And then every vertex that's not reflex, you kind of delete an edge, or more than one edge to make it form reflex angles, I think that procedure should show that they exist. But maybe there's a little bit of work to be done. But we'll move through some other things which will make clear that these things exist. Yes?
A very similar question. Like, is the condition R equals N equivalent to every vertex meeting a reflex angle?
Yes. Yes. Yeah. So if you think about it, how many reflex angles can, oh, sorry, I'm just, okay. Question was, is it clear that R equals N means that is equivalent to saying that every vertex has a reflex angle? And I think, yeah, that should be clear because if you have a single vertex, how many reflex angles can that vertex support? Just at most one, right? Because it's bigger than pi. And so, yeah, that should basically prove it. Okay. Right. So R equals N is exactly the same thing as saying that each vertex has a reflex angle. And then I think showing that these exist is not too bad. It's a little bit of thing, but yeah, we'll also see other proofs of why they exist. Okay, but let me give you some terminology, and then we'll do a few more examples just for fun, and then we'll see, yeah, see some other things. So terminology, and then I'll give you some history as well. A vertex in a planar graph, I'll say, or maybe I'll say in a pseudo triangulation. You can of course make this more general. Is called pointed if it has a reflex angle. Okay, so this is just a name for vertices, and I'm saying that I only want to look at pseudo triangulations in which every vertex is pointed, and so those are called pointed pseudo triangulations. Okay, so and this is really a lot to write, so I'm going to abbreviate it to PPT in a minute. Pseudo, maybe I'll write the whole thing. So we'll be talking about PPTs. Okay? A pointed pseudo triangulation is a pseudo triangulation in which every vertex is pointed. What was I going to say? Oh yeah, sorry. And from the count that we did previously, we see that a PPT on endpoints has exactly 2n minus 3 edges, just like a normal triangulation. And also note that if you had a convex configuration to begin with, then a triangulation is the same as a pointed pseudo triangulation. Okay, so if that's not obvious, I'll let you think about that for a minute. But if the arrangement is already convex, then PPT is the same as a triangulation. Okay. So this is a strict generalization of what we had before. So that's nice. And now let's do a couple more examples. Just to show you some of the properties here. So if you start playing around with these, and I encourage you to do that. If you start playing around with these, you will notice that you are in fact able to flip every internal edge. So here's what edge should I try and flip? So if I try and flip this edge right here, if I delete it, oh, sorry. I can add in this other one. And you can verify as we go along that, in fact, that's the only one you can add. Is that, I see some faces, confused faces. I haven't told you how to flip yet, but I'm claiming that if I delete the edge that I deleted, there's only one other edge I can put in to form a PPT. Okay, so I can keep going a little more. So I could maybe, so in here, of course, this, like inside of this little triangle, the situation is what it was before. So if I delete this edge, you already saw that I could flip some of these. So I could do something else. So this is mysterious to me, at least. It's not clear what's going on. So some of these flips are easier than others because, this one, the one that I just did, was just a kind of convex flip, right? So the thing that I just flipped here, this edge borders a convex quadrilateral. And so the flip is literally just the other diagonal. Okay. But some of them are maybe not so obvious, like the edge that I deleted here, if I remove this edge, the two things on either side don't form a convex quadrilateral. They form some crazy figure, and so it's not clear that it should have a flip, but indeed it does. So this is actually part of the exercises. So it's a proposition that every, and maybe this is proposition which will be covered in the exercises. Every internal edge of a PPT is flippable, uniquely flippable. So this actually, like, even though we moved to some crazy thing called pseudo triangles, you actually get back the number of edges and you get back flippability, which is really nice. I'll say a word about why. So this, again, if you read the exercises, you'll see, but here's a little hint as to why or what makes every edge flippable. So the idea is, if you delete one of these edges that are on the inside, it borders two pseudo triangles. And the union of two pseudo triangles, at least in general, except some degenerate cases, is going to be a pseudo quadrilateral. Okay, so it's going to be like this figure right here, which is a figure that has 4 vertices on the convex hull. And so quadrilaterals have 2 diagonals, and pseudo quadrilaterals also have 2 diagonals. And so that's the idea. Somehow you're like you're still doing a diagonal flip, but you have to make sense of like why this flips to that. But it's not too bad. It's not too hard. So it's kind of fun. So this is cool. So then you have this flip graph, and also the flip graph ends up being connected. So as before. So this is super nice. And let me say, so I have 5 minutes. So let me say a little bit about the history and a little bit about kind of where we're going next. Okay, so the history of this. Did I? Oh yeah, I don't think there's an edge in these two, actually. I haven't drawn the full flip graph. Sorry, this is just a portion of it. Yeah. Yeah, I mean the full flip, like, okay, finding the number of pointed pseudo triangulations is it's not, so if you write down a generic configuration and try to compute the number of pointed pseudo triangulations, I think that's like an open problem. I don't think there's a formula for that in general. So that's so the history. Actually, maybe I'll just say the history. Sorry. So the history of this stuff is that these pseudo triangles, I think, came up in the 80s in like work of Pocciola and Vector. So I haven't read those papers, but there's computer scientists who were doing kind of like visual angles or something. I mean, what you can see and how much you can see, the kind of art gallery problem, that sort of thing. And they came up with these pseudo triangles to solve a certain problem in that realm. And then, people didn't really think about them. But then around the late 90s, 2000, early 2000, Ileana Strainu actually used pointed pseudo triangulations to solve something called the Carpenter's rule problem. So I'll talk about that later, but the history is, I hope I'm spelling this right. So, and then Strainu from 2000s essentially studied this, and then other people built on her work. So there's papers of like Günter Rothe and Santos and Strainu. And then others. And then I'll say a word about where we're going next. So actually two things. So one is that I defined all of this stuff for generic configurations. I haven't said anything about degenerate configurations yet, so I'll say that next time. And the second thing is that, okay, I mean, we did all of this combinatorial stuff, and it's not clear why it's useful in any way. So the next thing that we're going to do is we're going to look at kind of two ways in which pointed pseudo triangulations show up naturally so the first one is going to be the theory of rigid motions in the plane. And so the idea is like a rigid motion, you should think of a graph like this, like a pseudo triangulation, for example, as points and rigid rods. Okay, so each edge is thought of as a rigid rod, and then you say, okay, here's my system of rigid rods. It's a framework. Can I move it rigidly? Does it have any rigid motions? Meaning I'm not allowed to shrink or extend the rods, and I have to kind of move. So you have to think of them as like robotic arms, right? And think like you have to think about like, can I, given a framework like that, can I move it rigidly or not? And pseudo triangulations, pointed pseudo triangulations play a role in that. And then the other thing, well, I'll mention it when the time comes, but I do have, I don't know. Okay, I have 1 minute. So maybe I'll quickly say something about degenerate configurations, because I think it fits naturally into the story. And if I don't have too much time, I'll come back to it. So I'll just give you a quick hint as to what to do. So for simplicity, I'm just going to look at points on a line, okay? And I won't give you the definition right now. I will simply draw some pictures, and then we can think about definitions if we need to. So what I want to do is I want to think about like triangulations and pseudo triangulations of configurations where points might lie on a line. And now I have to like let go of the idea that I'm only allowed straight line segments. I need curved arcs. I basically have to, right? So I'll draw you some pictures, and then we can discuss more about this tomorrow. But I'll leave you with some pictures to stare at. So I claim that this picture is a picture of a pointed pseudo triangulation for a degenerate configuration. So you're welcome to try and make sense of this. And I'll draw one more. Okay, fine. And then I'll stop. Maybe maybe it's not going to be anything fundamentally different from what I've drawn. Oh well. I guess it's a reflection of the other one. But anyway, yeah. So these, I claim, without any sort of explanation, that these are pointed pseudo triangulations of degenerate configurations. And we can talk more about that tomorrow. Okay, thanks. Yes.
So is general condition just mean
No collinear points, no 3 on a line. Yeah. That's an excellent question. The question was, is there a nice formula for the number of edges? No, wait.
In the previous case, we have 2n minus 3 was the formula.
Mhm.
Because we found the formula. Which was translation. Is there a nice formula for the number of faces?
A question, is there a nice formula for the number of faces? The answer is yes. I'll leave you to work that out. I mean, I didn't write this, but the calculation that we just did previously should also pop out a formula for F. Yeah. Yes, Chris?
Like together, like can you do all of the configurations at once? Like within the space of all the point configuration, somehow like, track of its constant even processing again.
Yeah. Okay, so the question was, can we look at all of these together, meaning look at all possible configurations of points, and then since the number of edges doesn't change, is there some nice connection, like if you move from configuration to configuration? And that's an excellent question, which is foreshadowing day 5. So we'll try to get there. Yeah, so exactly. So this is another thing that I want to emphasize. The number of edges does not depend on the configuration, and therefore you are welcome to try and change configuration and see what happens to pseudo triangulations. And actually, you should all try this. It's a lot of fun. I mean, imagine that you have a configuration. Take your pointed pseudo triangulation. Imagine that they're made out of strings this time, not rigid rods, and move points around. Drag the strings with you, and see what happens. Yeah, but we'll do a version of this probably day 4 or 5. Any questions from Hawaii?
Just the confirmation that we can hear Hawaii. Hey.
There's no questions here.
Okay.
Well, then, thank you, Asilata.